My name is Kevin Peterson. I assume this is recording now. And this is a presentation about writing a motor controller driver, which you can see from the slide. The software that I will show at the end of this presentation, so that we don't have to swap between displays poorly, is a pre-built IOC that you can download from the URL at the bottom of this slide. The controller is pictured here. Since it's virtual, there's nothing really to show you. And it is very easy to run on Windows and reasonably easy to run on other platforms. This presentation assumes that you've used the motor record before. You have some programming experience, and you can see some C compile errors there because semicolons were omitted, and a controller for which you have some documentation. You can see, you probably can't read that, and you're not supposed to be able to read that. That is a list of the MM4005 commands. That's just one page from the manual from the Newport controller, an overwhelming list of commands. So our standard approach when we tell someone how to write a motor controller driver is to make sure they have the documentation for the controller, to point them in the direction of a similar controller, tell them to use it as a starting point, and say, just implement the base methods. Now, this always reminded me of an internet meme because it feels a lot like this. You're telling someone what to do, and you're expecting them to essentially just know how to do it, and you're not really helping them along the way. So what I would like to do, because when I know that there is a lot of good documentation for ASIN motor, and you've seen it in prior talks. You can see a list of things here. But I always felt like when I had to write my first ASIN motor driver, and even the second or the third, that I didn't really have a good feel for how what I was writing fit in to the control system. Because I knew that I could click buttons on the MEDM screen, and I knew that commands got sent to the controller, but I just didn't have a good feel for what happened in between. So when we set up our IOCs, we're basically laying a lot of the roadmap between the driver, between the record and the controller. So when you set up your communication port, you're defining an ASIN port driver. And when you create your ASIN, when you instantiate the driver, you are tying the driver and that communication port driver together. So that's the link between those two. When you load your substitutions file, you are linking more things together. So you're loading an ASIN motor database, and you're passing it a D type of ASIN motor. That is where your motor record gets associated with the device support for the ASIN motor device support, dev ASIN motor.c. You pass it the port here, VMC1. That is where your motor record gets associated with the driver that the driver that you created right up here. And so this just puts all of those things, and I should move the mouse out of the way. This puts all of those things on a single screen so that you can see them simultaneously, because usually you're editing these files one at a time, and those links are not always apparent. So just knowing what you do to set up your IOC, your roadmap like this turns into something a little more defined. But there are still some question marks in the middle, because the ASIN motor architecture abstracts away some of the important details of what happens. This is great from the perspective of implementing things for the end user writing the driver. It's not so great when you write your first one and you don't really know what's happening behind the scenes. I've looked through the source code, and I'll fill in the blank for you, but it's the base classes that hide the functionality that helps complete this link. So it's helpful to walk through an example of something that the motor record does and see what happens at each layer. And so we will use the set position command as an example. So when you set the position from MEDM, you get the channel access call to the motor record, and the motor record has a load position function, and it creates, or it calls this code that you see there that tells device support to write a load position message, and it passes the argument to device support. Device support catches this request and translates it into a motor position call, which is something that the base class understands. At this level, there are a couple asyn queues. The commands get put on one asyn queue, and then when they come off of the queue, they actually get sent to the asyn motor controller port driver. The asyn motor controller port driver also catches this function, and this is where the set position method that you implement is actually called. So this base class already has code that says call the axis's set position method. And so your driver implements set position and it knows what to send to the controller. Why is this important? You can read why I think this is important. I'm not going to read them all to you, but it's important to point out the last one. With older architectures, older motor architectures, it was more straightforward to use debuggers to see what was going on. And with the asyn queuing of the current architecture, you frequently run into a spot where your thread of execution ends. And if you don't know that that command is being passed off to something else, it can also sometimes be hard to trace what's happening. So, you want to write a driver. Which of these do you need to implement? I don't know about you, but that's an overwhelming list for me. The motor record has a fixed number of commands that it sends to device support. So for a very basic asyn motor device driver, you really only need to implement things that the motor record can send. And so that shrinks the list of methods to a much more manageable number. My virtual motor controller that is used in the demo IOC implements fewer than the ones that the motor controller, fewer commands than the motor controller sends. And so things that are grayed out, because I have not implemented them, when the motor record says do these things, by default, I inherit base methods that do nothing. So the advantage to the asyn Model 3 architecture is my laziness is rewarded by good default behavior, which is basically none behavior. Okay, I would argue that your driver will be usable. You don't even need to implement everything that I've implemented in the virtual motor controller driver if you implement only these methods. And there's an asterisk next to set position, because if you fail to implement set position, autosave will not restore your position. So you could say that that's a necessary feature, but your motor will move and stop and tell you where it is if you only implement these. The report functions, the report methods are convenient, especially when debugging or when trying to figure out, is this motor configured properly? But strictly, they're not necessary. The base classes that print out very little information will get the job done. I can't show you the commands without breaking the display, so we will do the demo at the end. The virtual motor controller has a very simple set of commands, and they're all documented in a text file that comes in the documentation directory of the IOC, which you can pull up while you watch this presentation. You will see them in the source code that follows. When you are writing a motor controller driver, it is very convenient to see the communication to confirm that things are working properly even before you actually turn on power to the motor. So for this virtual motor controller driver, it's useful to have the Trace IO escape mask on, Trace IO escape bit set, and the driver bit set, so that you can see output like, oh, that goes the wrong direction, like this, and you'll see some communication. And the interesting thing about having the escape set, the escape bit set, is that you see the carriage returns and line feeds in your communication. If you find that your communication is failing miserably, there's a possibility that your terminators might be wrong, and this is a great way to see what's actually happening. So when you get down to writing your driver, you are probably going to copy from another driver, because that is a good way to start. I won't get into the details of the constructors. I will only point out that simple drivers in the controller constructor will create the virtual motor access objects. And for simple controllers, this can work because there's no additional information that needs to be passed to the access constructors. But for more complicated controllers, where there are values that can change per axis and the controller cannot determine them, you cannot create the virtual motor access objects in the controller constructor. You need to create them in your CMD file, and you need to pass it. It's your responsibility to pass it the values that it needs. A great example of this is the XPS controller. The XPS axis constructor needs the name of the axis, the string that you find in the controller's configuration itself, and also the number of steps per unit, because the controller communicates in engineering units, and the driver doesn't know what the MRES is. The axis constructors, again, there is other ASIN documentation that covers this reasonably well. The virtual motor controller code doesn't do anything special in these constructors, but if you have a controller that needs the CNEN field of the motor record to work, if you need to disable or enable torque and have that call a function in your controller, these MSTA bits need to be set here in the axis constructor. That's, I believe that the only time you have to set them is before the motor record is initialized at IOCNet. So now I'd like to run through some of the virtual access methods, but with a focus on where the values that your methods that you're implementing, where the values actually come from. You can see here, there will be some themes in these methods. In almost every method, you'll create a string and you'll write it to a buffer in the controller's private member area, and that will be written to the controller by calling either a write controller method or a write read method. For the virtual motor controller, I purposefully made it respond every single time you send it a command, so all of the calls in these examples will say write read. But if your controller doesn't respond, which is also very common, you would call write controller instead of write read. So when I documented this method, I wasn't sure where the acceleration actually came from. And I have since looked at the code and found the motor record doesn't actually send an acceleration when you click stop. The device support doesn't actually send an acceleration when you click stop. That acceleration comes from the ASIN motor base classes. That's an interesting tidbit. It could have functional implications if you decide you actually want to implement a stop deceleration but most drivers don't actually do anything with that argument. So I point that out, but we will move on. I would have implemented poll first because I think poll is crucial to seeing what's going on once you're developing the driver. But because safety is most important, we started with stop. So you see that we're sending the controller a command. We're parsing a response, and we are setting a parameter that tells the motor record through the various layers what the actual response was. Whoa, that broke. Thanks, Mac. Okay. Are they all broken? Just that one. So we missed the slide where you send the status command, but that's not particularly interesting. After you send the status command, you parse the status command, and the status command is parsed on various lines because most controllers respond with a number of some sort, and the bits of that integer are important, and it's your job to know, based on the controller's documentation, what the bits mean and set the appropriate parameters so that the motor controller's status can be set properly. The most important of these is motor status done and motor status moving. You can leave off the limits. You can even leave off the direction, although that might throw off limit stuff, but probably not. But you can't ignore done. The motor will not behave properly unless it knows when it's done. If your controller doesn't have a done status bit, you need to simulate it somehow. And I don't have a good example of that at the moment, but I can find some if pressed.
Have you ever seen that happen before? Or
Yes, I have seen a controller that doesn't have a done indicator. We'll call it a motor controller in quotes. It was an endpoint C300. It drove piezos, and it functioned more like a temperature controller with a set point than a motor controller. So you told it to go, there was no speed, there was no acceleration, there was no status. So I simulated when it was done by comparing the target position, and I had to set a window and said if it was within this tolerance of your target position, it must be done. The beamline found that wasn't fast enough because you're now at the mercy of the polling rate. So we implemented some stream support that set the position and didn't care about the response so that they could scan faster. At the end, you have to call param callbacks, otherwise the motor record doesn't know what's going on. And that one's broken too. I don't know why these are broken. You have these slides if you downloaded the zip file recently in the documentation directory. I don't know how I can fix that. So, wow, that's just all kinds of broken. I was doing something similar with the motor method where we talk about, I highlight where the arguments are used, but the important thing you can actually see on the slide, which is it's the position's relationship to the motor record fields. So in the move command, and there's an issue with this, in the move command, if you're doing an absolute move, your position is rval or dval over mres. If you're doing a relative move, that is not what it is. What you will find with the example IOC is you can't do a relative move. So if you do a relative move in the motor record, it will send an absolute move to the controller. Because use encoder is not yes, use readback is not yes, so it just doesn't use the relative move command. But if it was going to do a relative move, it would probably use RLV over mres as the argument for that. The base velocity, every time it's passed, is almost always, I believe it is always, the V base field over the absolute value of the mres. This is important because the mres can have a negative sign. Another important thing which I did not change here is that while it's called base velocity in the motor record, in a lot of the drivers, it is referred to as min velocity in some methods and base velocity in others. And so to mentally prepare you for seeing other drivers, I did not change this to make that consistent. The move velocity is the velo field divided by the absolute value of the mres. This is not the case for other velocities that are sent to your driver, and this is probably the velo that is the most obvious. Your acceleration, because your acceleration is an acceleration time, this acceleration is the previously calculated velocity minus the previously calculated base velocity. So it is the velocities already corrected for mres, so already converted to steps per second. So many of the drivers will use a send, accel, and velocity method, which is internal to your driver, because all of the move commands are going to set the velocity and the acceleration, and you don't really want to have to this saves code. You can just call this method and it does the job. This is what it looks like for the virtual motor controller. So base velocity is almost always the same, and broken slides. Your velocity is different, and we will see that on the next few slides, depending on what called send, accel, and velocity, and same with acceleration. So if you want autosave to restore your position, or you want to be able to set the position from the MEDM screen, you implement set position, and it's fairly straightforward. The position in your dial units are converted to counts, and the counts are set to the controller. One thing you might have noticed is that there isn't much here in the virtual controller methods, and that is because the virtual controller was written to accept basically everything that the motor record sends to you without modification, so that this could be as simple as possible. The jog command is called move velocity, and the thing that you will notice here, broken slides, is that the velocity, the max velocity, which is your jog velocity, is a signed number, and it's signed based on which button you press. So this signed max velocity is sent to the send, accel, and velocity command, and it is also sent to the jog command. This is not a problem for the virtual motor controller, because when the send, accel, and velocity is sent, the virtual motor controller takes the absolute value of the velocity when it's setting its controller's velocity. And when it gets the jog command, it knows that it doesn't need to take the absolute value of that. A signed value is acceptable. But if your controller can't handle being sent a negative velocity, then you can't do it this way, because it will break your send, accel, and velocity command. It'll send a negative velocity, your controller will give an error, and then everything will fall apart. This is a wonderful time to point out that the acceleration in the motor record, the jar field, is an actual acceleration, which is why the calculation is simpler. If you recall, for the move, it was desired velocity minus base velocity divided by the acceleration time, and here it is simply jar divided by the absolute value of the engineering, that should say mres, not EGU, and that's what happens when you don't get enough sleep. The virtual motor controller does not implement the home method because it wasn't obvious what that would mean or how that would work. But I wanted to show you what the arguments were in terms of the motor record fields anyway. Base velocity or min velocity is what it usually is, V base over absolute value of mres. The home velocity is that velocity on one of the other setup screens that you can't easily access, but it is important because it will not use the normal move velocity when this method is called. And the acceleration time is taken into account when you are doing a home motion. This forwards argument is not set by the motor record. In the motor record, you are pressing either home forward, you are writing to the home forward field or the home reverse field, and device support is setting this value for you. That probably doesn't have any practical consequences, but I find it interesting that that's the source of that. So that went a lot faster than I thought. I will do the demo in a moment. I think that the virtual motor controller, because it is so simple, because it was designed to accept everything that the motor record and device support handed by default, it makes a better starting point than some of the actual controllers that we generally refer you to, because the commands are simple, they're well documented. You don't need to understand the nuances of another controller to begin gutting it and doing what you need to do. Like there's a lot less to remove before you start writing your own driver. I'm trying to make what was difficult for me in the beginning easier for other people. So, on that note, this should be changed to here. The virtual IOC is running. What I wanted to do during the presentation, but I could not, is just show you a few very quick things. So this IOC is a little different than the default configuration in that I've turned off idle polling. I have increased the move poll rate to 1 second so that it is easier to see commands sent with polling. And I believe that's it. So we are going to turn on, that's not the right one. You'll notice I don't have the MEDM fonts installed, but we'll have to cope with that. So we are going to look at the escape asyn trace. If I click status update, you see the commands being sent to the controller and the responses, the position query, the status query, and the values that the driver has to parse in the poll method. When I click stop, let's make some space, you see the stop command being sent. And I have to keep changing focus. When I move the motor, and let's make a small move, you see the base velocity being sent. Let's see, you see the base velocity being sent, and the mouse, I can highlight that here. You see the velocity being sent, you see the acceleration being sent, and the move command, and then position queries. So one interesting thing to note, when you change the speed, you don't see that speed being sent to the controller. Nothing happens. If you change the acceleration, you don't see anything change here. Nothing gets sent to the controller when you change that acceleration. You only see that take effect when you move the motor next. And you can see that those values are different than they were before. That is another subtle point that is not an issue under most circumstances. But if you are setting these values and moving them from a different, if you're not using MEDM to move the motors, you might have the expectation that those velocities actually took effect when they have not yet. So from the front panel, if the front panel uses the standard motor velocity, if you have yet another creative asyn port driver way to communicate with the device that doesn't use your driver, it's something that you need to be aware of. I'm trying to think. Jog. So the interesting thing about jog is when you hold it down, you see the move happen. And when you let go, you can see that the motor record sends the stop command. So that is how your jog aborts. Home does, well, some of the buttons that are not implemented result in the driver doing a status update. So I don't have a home method. Nothing actually gets sent, but that causes it to pull. That causes it to move somehow. I don't know why that was. Bug in the system. That's pretty much it. The virtual motor controller doesn't do very much, and it doesn't do very much on purpose. Although there are a few more things it could do in the future that would make demos more useful. It would be useful to add parameters to it, to set limits. It would be useful to make an engineering unit line.